Okay, for part C, we're finding the time required for the wheel to stop spinning. And for part D, we'll find the number of revolutions the wheel will turn during the time it takes to stop completely. Okay, so once again, we are working on we have only two equations, right? Velocity and the position. So since we are trying to find the time when omega is 0, let's use the omega equation then. And we are saying that omega is 0 at the end and setting this to 0 then. And solving for time, pretty straightforward. Again, alpha is negative. Omega 0 needs to be taken in radians per second, not revolutions per minute. So we can get the time in seconds. Okay, and so this is our answer here. I don't think I boxed my answers. Okay, did that one, and this one needs to be boxed as well. Okay, so for part D, again, we're trying to find how many revolutions we will have for this to come to a complete stop. That is related to the angular position again. So that might be a little tricky. Just like try to understand what is it asking for, and with these practices, hopefully you know what to do. Initially, we set the theta 0 to 0, so that is gone. And we're just plugging the numbers. Omega 0 in radians per second is given here. And the time is, we need to use the time for the complete stop, right? Not 10 seconds, not 20, but the entire time. And again, the acceleration is negative, and at the same time we're using. And if you look at the units as well, it's in SI units, and this is going to give you radians. And this is what you're getting, but this is not the right answer because you need to convert to revolution. So we are getting rid of radians first by using this conversion factor. 1 revolution is 2 pi radians. And then we are solving for theta in revolution. And we are getting 26,170 revolutions. And if we look at the answer, in the first part, we got 283.7. So this should be much larger than that because it takes not 10 seconds, but 183.26 seconds, right? So you can also double check your answers that way. So these are the ones that I wanted to do. We added an extra part. You can also find the average angular velocity and such. So it's going to be in the solution. But it wasn't in the question, so you can simply find the average velocity as well in the form of change in angular position over delta t. And you know that initial theta is 0, and you have the final theta in radians, so you're using this one here, not the revolution one, and divide by 10 seconds if it is asking for the first 10 seconds, right? It's going to change here, so you're going to apply that. So this is for the first 10 seconds. This is the average angular velocity, and again, these are your conversion factors. So hopefully now you see the trend that these conversions are almost every time we need to use them if we need to convert from revolutions to radians and so forth.